When we created the scatter plot in StatCrunch, we saw that there was a line drawn in the data in such a way that it was a line that seemed to best fit our data set. That's what we're going to look at in this section. So when there is a relationship between two numerical variables, then we can use information about one variable in order to learn something about a second variable. So maybe you want to predict product sales for a month when you know the amount spent on advertising is $10,000. So in this case, the amount spent on advertising would be your explanatory variable, also called the predictor or the independent variable, and then why the product sales should be happening in response to the amount that you spent on advertising. So we would call that the response variable or the dependent variable. When calculating the correlation, we did not need to identify which value was the predictor and which value was the response. But now that we're going to be creating a line, then we do need to know which one predicts which. The equation for a line in statistics is y equals a plus bx. If you remember from high school, you probably had y equals mx plus b. Same idea, except here we start with our y-intercept. So that is that vertical intercept. It's the value of the y variable when x is 0. That sometimes has a meaningful impact on the data. Sometimes it's not a particularly useful value, but it does help us figure out where we need to start this line when x is 0. Then we add the slope times the x value. And the slope by definition is the amount by which your y or your response variable will increase when you increase your x exactly by 1 unit. You might remember slope as rise over run, and it is still that. It's how much your y value will rise when your x value runs specifically by 1 value. So the scatter plot that you obtain by graphing the x and y values will have either a strong, a weak, a moderate, or no relationship. When there is a moderate or a strong relationship, then you would want to try to fit a line to it. I want you to imagine where the best line would be to try to capture what's going on with those dots. Well, we could draw lots of lines in there. We could draw one line that seems to be going through the data for line 1. We could also draw something like line 2 where it hit the middle, but it really did not describe the rest of the variables. So how do we find the best line? Well, it's obvious here that line 1 is better. But what about these two lines? It's hard to tell which one is which line is actually doing a better job at capturing what's going on with the data. So we need to be able to calculate what the best line is by something other than just relying on our observations. So the way that we find this best line is we calculate what's called a residual between a line and each observation. So for example, if you had an observation 15, 44, and you had the line fitted there, y equals 10 plus 2x, when you plugged in 15, you would have 10 plus 2 times 15, or 40. So the line predicts the value 40, but the actual value was 44. That would be a deviation of 4. Now, for each of these deviations, if you were to square them, this line is going to minimize the squares of all of those deviations. It's actually a quite complicated procedure that you do to calculate this. It requires a decent amount of calculus to get these, to actually figure out mathematically how to do this. But thankfully, we have some formulas that have been derived to help us, and is also programmed into any statistical software package. You'll notice some of the deviations are positive and some of the deviations are negative. That's going to happen because a best fit line should have some values above the line and some values below the line. But what we're trying to do is we're trying to minimize the squares of these deviations. Part of why we need to square them is so that all of our values are positive, but there's also some other mathematics going on behind there. And you'll just have your formulas and your statistical software. This formula should look absolutely horrendous, but this is the way that you calculate the sum of the squared deviations. You take each observation, you subtract the prediction, and you square it. That is very time consuming and quite difficult, but it will find this least squares regression line, and that's going to be the line that's going to minimize that sum of squared deviations. The formulas have been derived here. They're still somewhat cumbersome. The slope, you have to take each x, subtract the mean, each y, subtract the mean, multiply those two together, then add all of that up. Then you divide by the sum of the x minus x bar squareds. Now that's actually a different value than the x minus x bar that you had above, because you're squaring and then summing. It's complicated. You will not do this by hand. The y-intercept is much easier to calculate. It is simply the y-average minus the slope times the x-average. Turns out that the average of the x's and the average of the y's will always be specifically on the regression line. Looking back at example 4.2, where we calculated R and the scatter plot using StatCrunch, I just want to point out that what we did in that part is exactly what you need to do in order to get the regression line. It will be up here on this line, and it will use the actual name of the variables and not a generic x and y. If you would rather, you can get A right here next to the intercept and B right below it for the slope. So it's given in two places. It's given as an equation or here in the table under these estimates. There is a multiplication that's happening between the slope and the x variable. So if you are going to make some predictions like we'll do in a later section, that is a multiplication that's happening there.